Hi folks, this is David Villar and welcome to the second video on pesticides. Here we're going to discuss properties that determine the environmental fate of pesticides. And I wanted to show you how the National Pesticide Information Center considers the movement of pesticides in the environment based on their physical-chemical properties. So they use the following properties: water solubility, half-life, groundwater ubiquity score, binding affinity to soil, and vapor pressure. So the first one is water solubility. They basically divide it into low, moderate, and highly soluble. Just like sugar and salt, if they're highly water soluble, they will dissolve easily and they can travel with water in the environment. That means traveling downstream of a river, a creek, and the probability of reaching groundwater is obviously higher. They are also more likely to be absorbed by the roots of plants, and if you were exposed topically, they are not likely to be absorbed through the skin. If they are poorly soluble, you can think of oil and water. Even if you mix them, they're not going to mix very well. The second one is half-life. This is the time it takes for a certain amount of pesticide to be reduced by half. This happens as it dissipates or breaks down in the environment. In general, a pesticide will break down to 50% of the original amount after a single half-life. After two half-life, only 25% is going to remain, 12% after three half-lives, and this continues on and on until the amount remaining is nearly zero. The problem is that the half-life will vary a lot depending on the conditions in the environment and at different speeds depending on whether it is soil, water, plants, sediments, or any other matrices. So why is the half-life important? Well, basically it's going to tell us if the pesticide is going to build up in the environment. In general, it is considered low if it is less than 15 days, moderate if it is between 16 and 56 days, and highly if it is more than 60 days. Obviously, if the half-life is long, the pesticide is more likely to build up after repeated applications, and that may increase the risk of contaminating nearby water sources, plants, animals, and you name it. What are the different factors that influence the pesticide's environmental half-life? Well, there are many things that play a role in how long the pesticide will remain in the environment. For example, the sunlight, the temperature, the presence of oxygen, the type of soil, the microbial activity, and all of this makes it really impossible to describe a single consistent half-life for a pesticide. It is not included in the table here, but we cannot forget about the product's formulation, which can also change how the active ingredient is going to behave in the environment. And you may also wonder what happens to a pesticide after they go away. Well, they just don't simply disappear. Instead, usually they become other chemicals that could be more or less toxic than the original one. And in most cases, they are broken down into very small pieces, which include carbon dioxide, water, and minerals, which is the only thing left after they break down. The next one is the groundwater ubiquity score. This is an index that indicates the potential to move towards groundwater. It is experimentally calculated by relating the pesticide's half-life and the sorption potential, which is abbreviated as KOC, which is basically the ability to bind tightly to soil. Basically, if the pesticide has a short half-life, low water solubility, and high sorption potential, it has less potential to move through soil. If the half-life is high water solubility and there is low sorption potential, it will have a greater potential to move through soil. The next one is the pesticide's soil binding affinity. This is also called the sorption coefficient. In other words, it's the attraction between the pesticides and the particles of soil. And as you may imagine, the strength of the attraction varies a lot depending on many complicating factors, Some of them depend on the environment, other ones depend on the chemical itself. And as we can see on the right figure, a high KOC of more than 10,000 implies that it binds tightly to soil. Between 1,000 and 10,000 is moderately bound, and below 1,000 it does not really absorbs to soil very well. If you want to remember something, the more sand and silt a soil has, the less attractive it is to an organic pesticide. And this is because sand has very high, very many large particles, and there is no place for the pesticides to bind. By contrast, clay soils are made of smaller particles that are electrically charged with many layers that can attract organic matter, and that means that many of the pesticides will be attracted to bind to those particles. So basically, soils that have more organic matter and clay are better able to hold on to pesticides. And the final one is the pesticides vapor pressure, which is the tendency to evaporate. In other words, to change from a soil or liquid into a vapor. And as we can see on this figure, the pesticides with low vapor pressure, like permethrin, are less likely to turn into a vapor and get into the air. And those that have a high vapor pressure, like sulfuryl fluoride, are more likely to get into the air. And you will typically see vapor pressure measured in millimeters of mercury at 25 degrees centigrade, which is the same as 77 degrees Fahrenheit. We can see what we see in those chambers when you place a pesticide in a container and close it, is that some of it will stay at the bottom and some of it will evaporate into the air inside the container. And basically the pressure from these trapped vapors pushing outwards can be measured with pressure gauges or any other devices. And as we can see on this other slide, there are many environmental factors that will also affect the volatility of a pesticide, apart from the vapor pressure. For example, the water solubility and the ability to stick tightly to soil. The more water solubility and the ability to stick tightly to soil, obviously the less likely it is to volatilize. If it does not really dissolve well in water and does not bind to soil, it is more likely to vaporize. And as we will see with atrazine, when pesticides move off from the application site as vapors, they can be carried away by air and they could later deposit with rain onto soil, water, plants far away from the site of application. This is actually called vapor drift. Now the criteria for to indicate that a pesticide used as directed has the potential to cause adverse effects on non-target organisms. Basically, it requires a risk assessment that includes both the toxicity of the pesticide on the non-target organism and the level of exposure they are likely to encounter in the environment. So here is the table that EPA uses to consider how toxic a pesticide is on an acute basis, which is similar to what we already saw in previous videos. On this table, the acute toxicity is included for aquatic organisms, which is expressed in terms of lethal concentration that kills 50% of a population. And for terrestrial organisms, they use the LD50 in the diet or a milligram per kilogram basis. Next, they will estimate the risk quotient to come up with an ecological risk assessment. And the equation includes the exposure or the estimated environmental concentration. And as we just saw, the toxicity, which is the effect level or endpoint from an ecotoxicological testing. For example, the LC50 or the LD50, or ideally a no observed effect level. After they come up with the risk quotient, that's compared with the EPA's level of concern. For example, if we use an LC50, that level of concern is 0.1. In other words, the concentration in the environment should be at least below 10% of that LC50 to be considered as a safe for most of the population. Obviously, this type of assessing the risk is not including chronic exposures, only acute ones. As an example, if the estimated environmental concentration is 5 milligrams per liter, and the LC50 of a particular for a particular fish species is 50 milligrams per liter, the risk quotient would be 0.1, which would suggest there is no high acute risk concern for that species. Ideally, as I say, we should consider endpoints for chronic exposures if the pesticide is going to be present in that environment for a long time. And we will discuss specific examples on the next video on herbicides. So until next one, thank you guys for listening, and goodbye for now.